Good morning. It's been a long time. I've missed you. Um, Thank you for your patience while I was sick, and now I'm still getting over it. We'll see how I fare. Um, it's been just crazy. But uh let's see here. Number one thing is if you've started working on um the lab for this week, one might be very difficult because we haven't started the material yet. And two, I had to adjust some code because it was marking too generously on the first couple of parts. And so I just want to show you what I mean. So if you've started, you might have to go back and just make sure that those first couple of parts are actually correct because otherwise it'll follow you through. Let's see here. So here in question one, the um it was marking too generously. Okay, and so in this very, very first part. And so I fixed that and then I rescored them. And so just go back and make sure that you have the right answers there and then it should be all good. Okay? Um but like I said, kind of tricky because we haven't started chapter 5 yet, and that's what lab 6 is all about. So it's not due until March 10th. And so you've got time to work on it. So if you haven't started, that's totally fine. Okay, where do I go from here? I feel like there was something else I wanted to say. Oh yeah. Um You had your test. Good job. You should be able to. So I always go through and check work if you've submitted work and just kind of see if I see any typos, right? Because it's marked wrong, but it should be marked right. Just maybe, you added a 0 or something. Then I always go through and add marks. Whenever I do make adjustments to your grade, which is always up, never down, because that would be rude. Um, and so whenever I make adjustments, I just put it in the feedback. Now, I don't know what it looks like on your end. I can't seem to figure out how to get into student mode through Moodle, so because it clunks out. Uh, and so you should be able to see feedback if you go back into your test. So initially the test was closed off. You couldn't get back in there to see what it was like until I had graded them and then I released them. I also made it out of quite a few less points. I can't remember exactly how many. Um, but just because it was a little bit long, which is so for online classes, I do make them longer, right? Just because it's open book and it's you're meant to keep your pace up and just in terms of kind of fairness to in-person sections. So I do make them long, and then I'll scale it back if I need to. Okay, so um, yeah, but really good work. And now we're ready to start chapter 5, my favorite chapter. Well, the start of my favorite chapters. And so we kind of got through the boggy parts, and now here we are on the other side. Uh, let's see here. Um, feel like there was another thing, another kind of housekeeping thing that I wanted to bring up, but let's see. That's okay. It'll come to me. I'll keep an eye on the chat if there's something that you remember that I should have mentioned. All right. Let me move stuff. I don't need the mouse, I don't think. All right. So we're starting chapter 5 today. Foundations for Inference, which, like I said, is my favorite part of this course. This is the meat and potatoes of the course and why we're here, why you have to take this course. or most people have to take this course as part of their program, and this is the reason why. Okay, so everything we've done so far kind of leads up to it, but we're starting chapter 5, which is called Foundations for Inference, but I'll just say inference. Okay. Now, this is section 5.1, of course. And I sent out an announcement and I said, hey, if you wanna get a head start, you can read chapter 5. And because no doubt it's going to be a lot. There's a lot of things that we haven't seen before. And so it's nice to have read ahead if you have a chance. Now, inference. Inference is what statistics is all about. Okay, and so inference, and maybe I'll even do a pink pen because it's so important, right? Is when we use sample information to infer something about the population, right? But Emily, isn't that what statistics is? Yes, it is. They're the same. Okay, so statistics is at its heart inference. Okay, and so when we use sample information, and maybe to learn about the population. Of course, we can only learn about the population that we sampled from, obviously. But that's the whole idea. Now, there are multiple things that we can do here, but let's start by breaking it down. So remember, chapter 1, we talked about different variables, right? And we said, okay, there are two main different variables. We can have a categorical variable, or we can have a numerical variable, right? And so here, we can do inference for a categorical variable. Maybe I'll do a little arrow. Or a numerical variable. Okay. Now, what we're going to analyze if we have a categorical variable is a proportion. Now, we can talk about how one proportion compares to a number, how two proportions compare to each other, how three or more proportions compare to each other. And so what's a proportion then? A proportion is a count out of the total, right? And so here, for categorical variables, we analyze proportions, or I'll put the S in brackets. We're going to start with just one proportion, and then we move to two proportions, comparing those two, and then we move to three or more proportions and we compare those proportions. Now, what a proportion sounds like is when you see a commercial. We don't really watch commercials anymore, but when you see a commercial and it says 4 out of 5 dentists recommend Colgate or whatever, right? And so now you have some count, 4 out of a total 5, and now you have a proportion. Okay? And so for a numerical variable, now I have a number, which means that I can talk about the average, right? And so typically we're analyzing the mean, okay? But kind of, I'm gonna parking lot numerical variables because it's later. But when can we use the mean? If we have a normal distribution or an approximately normal distribution. So that's going to be one of the conditions. But for most things, we can assume a normal distribution. And so we'll talk more about that in chapter 7. But for numerical variables, where's my pointer? For numerical variables, we're going to analyze the mean or the means, but we're going to do the exact same thing that we do for proportions. I start with one mean and I can compare it to a number, or I have two means and I compare them to each other, or I have multiple means and I want to compare them to each other. Okay? And so this here, means is in chapter 7, and proportions is chapter 5 and 6. So how it's laid out is in chapter 5, bless you, uh, we start with just one proportion and we lay all the groundwork. Now, what's really, really fun about what we're starting, so about inference, is we're going to lay this groundwork and it's going to feel crazy. There's so much to remember. There's so many ins and outs, and buckle up. Okay? But what's really, really nice is once you've learned all those rules, okay, then those same rules apply no matter what type of question you're working on. Okay? And so I'm going to be talking about question types. Okay? So in chapter 5, we're going to be talking about one sample proportion. And this is the question type. Now I highlight that because that's going to be your main question to yourself on test 2, because we're going to be doing inference on test 2, but also on the final exam, right? Your first thing that you have to tackle is, what type of question is this? And then once you've decided what type of question you have, you're just kind of on rails. Then you follow the formula sheet, and so deciding what type of question you have is going to be a big part of what we're doing. Now in chapter 5, we're only dealing with one type. We're introducing all these concepts. I think of it as learning a game, right? And so you have to learn the rules of the game, which is why I like playing games, is I like to learn all the rules. The more complicated, the better, I think. And so kind of have to embrace it. So we're going to learn all the rules of the game, and then we're going to play all the different types of questions, and it'll be a breeze. Okay. So, let's see here. So that's kind of an overview. So chapter 5, we're going to focus on introducing all these concepts. And then in chapter 6, we introduce one proportion, and then we move on to 2 proportions, and then 3 or more proportions. And then we move into chapter 7 and we start with 1 mean, 2 means, and then 3 or more means, if we have time. Usually we run out of time, so that's why I say if we have time. Okay, so let's see here. If I'm going to use sample information to learn about the population, remember we had some terminology, right? So sample information, we can use maybe orange. I can use a statistic. A statistic is a measurement from a sample, right? So we use a statistic to learn about the population, but really what are we talking about? We're talking about the parameter, the corresponding parameter. Okay. Okay. So we're going to talk about statistics and parameters. Okay. Now, for one sample proportion, and I am jumping ahead in the slides because I don't know. Sometimes the slides work for me and sometimes they don't, and that's okay. But for one sample proportion, the statistic that we're going to be working with, the statistic is going to be the sample proportion. whereas the parameter is going to be the population proportion. Yeah? So, for example, something like 4 out of 5 dentists, right? Kind of a go-to example. Does that mean that exactly 4 out of 5? No. For the whole population, right? Does it reduce to 4 out of 5? No, but we expect it to be close to 4 out of 5, right? Whatever that is. Uh, 80%, I guess. Um, and so, right, the population is close to 80%, right? But not necessarily exactly 80%. We know if we took a new sample of 5 dentists, maybe 5 of them recommend whatever, Colgate or whatever. So we're going to need some notation for the statistic. And for one sample proportion, what we're going to use is we're going to use p hat. So it's a p with a hat on top. And there's a really funny note in the textbook. It's in the footnote. And because p hat, I don't know, you remember, there's a pH fat, which is like something cool. And then she says, like, this textbook. Anyways, pretty cute. It's worth finding. So here, p hat is the sample proportion. Yeah. Now, for the parameter, and if you kind of dig back in the archives, it was a long time ago now, and we had a break in between, and I was sick, and blah, blah, blah. But if we dig back in the archives for a parameter, we use Greek letters, right? To indicate that, hey, this is from a population. I don't actually know what this thing is. I think it might be this, right? And so for a parameter, we use pi. Typically, we should. So this is the Greek letter pi. Okay, but this is the one time where I don't use a Greek letter. I use p instead. So I just use a lowercase p or p. I use p to denote the population proportion. This is the only time where I don't use a Greek letter, and it's only because pi is a constant, right? So I don't want to get confused with the constant 3.14159, blah blah blah, 19. Doesn't matter. Right? And so here I use p for the population proportion. Okay? So then if we take it back to the very beginning, what inference is, right? What are we going to do? We're going to use the sample proportion, so p hat, to learn about the population proportion p. Okay? And so then inference becomes, we use p hat to learn about p. Okay? Now, there are 2 different things that we can do with trying to learn about p. We can try to say, okay, I have this sample proportion. How about I build some bounds around this thing? Because I understand that this is going to change every time I take a new sample in theory, right? And so, so we kind of build a buffer around this this estimate, okay? And so the other thing that we can do is we can say, well, how far away from 0.5 is this proportion, right? And so there's kind of two things that we do inside inference. But we'll hold off on that for just a little bit. And and go to this next slide here. So like I was saying, so we were often interested in these population parameters, and I'll highlight it again just in case. Right? It's been a while, right? So anytime we're talking about a population thing or a measurement from the population, it's called a parameter. And so what we're going to do is we're going to move away from calling the sample information a sample statistic. And what we're going to do, just to emphasize that this is my best guess at what the population looks like, we're going to start to use the term point estimates. Okay? So here, this means that p hat is a point estimate of p. Okay, it's my best guess. In fact, I'm going to write that here. The point estimate is my best guess at what p is. Okay. So we've taken a sample, we've randomly sampled, we're confident that we can assume that it's representative of the population. And in that case, right, then we can assume that this is my best guess at what the population looks like. Okay. What we're going to be dealing with a lot is that this idea that if I collected a completely different random sample, right, then I would get a different sample proportion, right? That's fine. Um, and so we have this variation from sample to sample. Okay. And so the term that we use to quantify, I guess I was trying to not use the term that they use here, but to quantify how much variation or how much variability we have around this point estimate, we use the margin of error. I often refer to it as a buffer. And so let's see here. So the margin of error is kind of like a buffer. Yeah. So, kind of one example that I use, which makes more sense when we have class in person. But if I ask you how far is it to your house, right? You understand that there's an exact measurement, right? If you had the proper tools and whatever, you could find the exact estimate. But we don't need to do that, right? And so for me, I would say, well, so I'm on campus now. How far is it to my house? I guess probably 5 kilometers, right? My best guess. Then what do I do? Typically, if we're kind of talking amongst friends, then I would say plus or minus, and then what happens? If I say something crazy like 10 kilometers, you would say, "Oh, that's kind of weird. Why why is your buffer so large? Are you not confident in your estimate?" No, exactly. That's what that means, right? And so, whereas if I said plus or minus 2 meters, right, you'd say, "Whoa, that's crazy. You're so confident in your estimate." Right. And so that's what that margin of error is that buffer, right? The plus minus, right? Kind of a plus minus uh, thing that we're going to have. Now we're going to have formulas for these, but I just want to talk about just the concepts because we know them, we understand them, we use them, but we never call them margin of errors. Okay? So here, just as an example, suppose we randomly sample 1,000 adults from each state in the US. Now, would you expect the sample means of their heights to be the same, somewhat different, or very different? So if we think about kind of an imaginary sample, what do I have? I have a state. I'll just go Washington, Oregon, work my way down the coast, right? Do 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 do. Okay. So what would this data set look like? Now I have the mean height, the mean of a sample of size 1000. Now, I don't know what these mean heights are, but I can denote them by an X bar. Now, this is a little tricky because we we said we're gonna talk about proportions. Emily, you said, but in chapter 7, we're gonna talk about means. And so part of what we're doing here in chapter 5 is just introducing the difference between proportions and means. Okay, but how do you know mean heights? Well, it has the word means. Okay. Usually we use means to introduce this concept just because it's easier to wrap our heads around averages changing, right? And so here, what do I have? I have X bar for Washington. I have X bar for Oregon. Now, I expect these to be similar, right? Because they're based off of a sample that's very large, right? And overall, we expect the heights to follow a normal distribution. And so there's no reason why these heights wouldn't be similar. Do I expect them to be exactly the same? No, right? Because we have this variability, right? And so I would expect them to be somewhat different, right? But similar. In fact, what do I expect them to be centered around? I would expect all these heights, all these average heights, to be centered on the population mean height, right? Right? Centered, whoops, on the population mean height. Um, Another example is you go to the vending machine, you get a bag of Doritos, like I often do, and there's a weight on the bag, right? It says it's supposed to be some weight. I can't remember what. Do I expect it to be exactly that weight? No, I expect it to be around that weight, right? But if I got another bag, I would say, hey, these are different. Not drastically different, hopefully, right? But I expect them to be somewhat different, but centered on the weight that's written on the bag. Okay. So this idea is what you're doing in the lab this week, where I get you to I give you the population, okay? And then you pull a random sample just to practice pulling a random sample in Excel. And then you can find your sample proportion and you can compare it to the population proportion because I have given it to you. Right? And then I repeat it. I give it to you 100 times over, and then we look at the distribution of those proportions. But I'm getting ahead of myself. Okay, so just reading this article. I'm going to skip some things, but I'll read the highlighted parts. Okay, and so uh, from some, doesn't say, oh, from Pew Research, which I think is really funny because I've got some beef with how they've written this, but that's okay. So a plurality of the public, so 41% of the public, okay? And so remember all that time we spent reading tables and things and talking about, okay, so of those who vote Democrat, right, how many blah, 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 right? So now we're back to that, and that's what we were practicing, right? So of the public, 41% believes young adults rather than middle-aged or older adults are having the toughest times in today's economy. So I'm going to highlight the part that interests me. Of the public, 41%. Now this is a proportion, Okay. And so what I'm going to do, right? So proportion, remember a proportion, maybe I'll write this down. Recall a proportion is a probability, which is roughly a percentage. Okay. Remember all these three P's are the same thing, right? So 41% as a proportion would have to be 0.41. And you're always going to use the proportion for your calculations. And so what can we do? We can say P hat for the public. Now I'm going to use these subscripts often, right? Just to denote where this information came from. It's not a huge deal when we're talking about just one sample, but eventually we're going to be comparing two samples. So then we have to be able to identify which group it came from. So it's good to just get started with that right away. So the sample proportion from the public is 0.41. Okay? It's my best guess at how the public feels. Right? Now, skipping to the next highlighted part, among all 18 to 34-year-olds, so of all these 18 to 34-year-olds, and this is where I don't like fully half, 49%, that doesn't make sense. So I'm just gonna approximately half. I'll just replace it with that. I just find it so grinding. Fully half, 49%. This makes sense. But that's just me. So 49% say they have taken a job they didn't want just to pay the bills, with 24% saying they've taken an unpaid job to gain work experience. Okay, so this 24% is also a sample proportion, but I feel like we don't use it, so I'll just hold off on it for just a second. But what can I do here? So this 49%, this is a sample proportion, but it's restricted to 18 to 34-year-olds. Oops, 344-year-olds. Oops. Is 0.49. So let's see here. And then I'm gonna skip the rest because it's just more proportions, but we're gonna focus on these two. Yeah. And so now we've got our point estimates, right? So here, this is my point estimate. Right? P hat for the public, 0.41. P hat for the 18 to 34-year-olds is 0.49. Okay. Now, right, we have our best guess. Now we build a buffer around it, right? And so now we need this margin of error. So again, just skipping through to the highlighted part. So the margin of the sampling error is plus minus 2.9 percentage points for results based on the total sample. So that's for the public. Okay? And so here, based on the total sample, which is the public. Okay? And then the buffer that we have for the 18 to 34-year-olds is 4.4%. Okay, and then here at the 95% confidence level. Now, I'm gonna pretend we didn't see that for a little bit, okay? Just a little bit. Okay? But so how we can write this is, okay, we've got our point estimate, 41% or 0.41, and then we have plus minus 0.029 or 2.9%. Yeah? And we're building a 95% confidence interval. okay, which we're not introducing yet, but we're kind of relying on it a little bit. But if we go back to how far is it to my house, uh, I would say, oh, it's 5 kilometers plus minus, I don't know, a kilometer. And then you would ask me the follow-up question, well, how confident are you? And I would say 95% confident. Right? The 95% also feels familiar in a way, right? Because we had the 68, 95, 99.7 rule, and that is what we're going to dig down to. Okay? And so here, fine, I guess we will do it. Let's see here. So the 95% confidence level, we will have a normal distribution and it will be centered on P or P hat is my best guess. And then I have this buffer here, right, covering the central 95%. Okay, so this distance is the margin of error. And this is the central 95%. Now we're going to build that out better in a second, but it is exactly going back to that 68, 95, 99.7. Okay, so what can we say? We can say, okay, 41 plus minus 2.9%. So then at a 95% confidence level, right, we can say we're 95% confident that 38.1% to 43.9%, right, just building out those buffers, going down a little, up a little, right, of the public. Okay? So it is of the public, right? Because my estimate was from the public and my margin of error was from the public. And so I can only talk about of the public. Believe young adults, rather than middle-aged or older adults, are having the toughest time in today's economy. And so we can do the same thing for the subgroup, right? We had a point estimate of 49% or 0.49. And then we said plus minus 4.4% or 0.044. So we're 95% confident that 44.6, which is 49 minus 4.4, right? To 53.4, which is 49 plus 4.4. So we're just building out on both sides. Of the 18 to 34-year-olds, have taken a job they didn't want just to pay the bills. And that's just the subgroup that we sampled from, or that we have information from. Okay, let's see here. Do I remember what I wanted to do? I feel like I wanted to skip this one, but that's okay. So suppose the proportion of American adults who support the expansion of solar energy is 0.88. Okay, and this is our parameter of interest. Now, here in this scenario, we're pretending to know the population, just like we are in the lab later, right? And so we're pretending to know what the population looks like. So here, pretending to know what the population looks like. Is a randomly selected American adult more or less likely to support the expansion of solar energy? Well, a randomly selected adult, I'm expecting them to be hovering around 0.88. Not exactly 0.88 necessarily, but so I was talking about the sample, but I guess here they're talking about is a randomly sorry about that. Is a randomly selected American adult more or less likely to support it? Well, if we're expecting 0.88, of the population to support the expansion of solar energy, then I'm expecting that a randomly selected American adult has an 88% chance of supporting solar energy. So they're more likely to support it. More likely, since we expect 88% to support. Got ahead of myself. There. Okay. So oh yeah, typo galore here. Nothing we can't fix here. So suppose you don't have access to the population of all American adults. How sloppy is this? And how sloppy of me to not fix it. Yikes. Which is a quite likely scenario. We're not going to have access to the population, but that's okay. That's why we have statistics, is because we don't need the population. Okay? Now, in order to estimate the proportion of American adults who support solar power expansion, you can sample from the population and use your sample proportion. I don't know why well, I do know why it's doing that, but as your best guess for the unknown population proportion. And so what you would have here, right, your best guess is your point estimate p hat. Right? So we take a sample and we find the sample proportion, and that's our best guess. Now, in theory, and I'm going to kind of zoom past this because we're doing it in the lab. I'm just kind of outlining the theory in the lab. But what we would do is sample with replacement, let's say 1,000 American adults from the population. And so you take a random sample of 1,000 American adults and you record whether they support solar power or not. There shouldn't be there. Okay. You're going to calculate the sample proportion, which is exactly what you do in the lab. Okay. And then you're going to have a collection of sample proportions, right? You can redo that many times, right? You can collect, so you collect one sample of 1,000 American adults, and then you record the sample proportion, and then you send them back out, and then you randomly select another sample of 1,000 American adults. Sure, there can be overlap, but not really. If you're randomly sampling, it's unlikely. Right? And so then you collect another sample, record the sample proportion, and then you send those out, collect another sample, record the sample proportion. All of a sudden, you're going to have this buildup of sample proportions. Those sample proportions are going to follow a normal distribution. I know, crazy, right? And so what you're going to find, if you plot the distribution of the sample proportions, then class, I don't know. Just in theory, if everyone did their own, right? We have a small class, so we'd have to do it a couple of times over. But this is just the R code. You can ignore this, but it's just if you wanted to play around with it and recreate it. But we do it in Excel, so you can skip that. What's going to happen though is you've got this collection. So now you have a sample of sample proportions. Okay? And this is called this is called a sampling distribution. A sample of sample proportions. Okay? So it's the distribution of the sample proportions. Now, this is a concept that takes a very long time to kind of wrap your head around, and it's okay. You don't need to fully wrap your head around it, but we are going to leverage the normal distribution. And so what we find is that it's approximately normal. Hey, it glitched out. Oops. Eee. Why is that so exciting? Means I can find proportions or probabilities associated with a proportion, right? So if I tell you just looking at this distribution, maybe just ignore the curve that I drew for just a second. If I told you that, hey, I found a sample that had a sample proportion of 0.88, would you be surprised? I guess I should use a 0.89, something other than the proportion, the population proportion. So I tell you, okay, I found a sample proportion of 0.89. Is that weird? You would say, well, where does 0.89 fall on here? Well, probably, somewhere around here. Is that weird? Not really. It's where we expect things to be, right? Because it's kind of towards the center. Now, what if I said, okay, I collected another sample and I found the sample proportion to be zero point 0.7? You would say, oh, that's strange. Why? Right? So just looking here at this number line, where's zero point 0.7 here? 0 0.7 would be way down here. So really what you're saying when you're saying that's strange is actually, well, the probability of that happening, if it's actually centered on 0.88, is very, very, very small. And so that's what we're going to be getting at, and that's what we're building towards, right? So we can use this distribution to decide if things are unusual or not. Okay? And so, of course, there's going to be a center, right? In fact, it's centered on the population proportion, P. We're also going to have a spread, okay? And so this spread is a little bit different, okay? But it's basically the standard deviation, okay? And so uh, we will also have a spread, okay? I'm holding off on just a little bit longer because what is this spread? Well, first let's talk about what is this distribution? Well, it's a distribution of sample proportions. So then what I would be talking about in terms of the spread, because it's approximately normal, I can say, okay, well, then I can use the standard deviation as an appropriate measure of spread. But then I'm finding the standard deviation of the sample proportions. And so we just introduce a new word called the standard error of p hat. Okay. The standard error of p hat, which is the the standard deviation of p hat. But we'll start with the center. So here we have the same sampling distribution. And what is the shape in the center of this distribution, which is what we already talked about? What is the shape? Well, it's approximately normal, somewhat bell-shaped. I would say it's really a nice normal distribution, right? And so, right here, I would say it's approximately normal. uh, And what's the center? Well, I guess it's on this next slide. The center of the distribution is about 0.88. Now, the reason it's so specific is because we know that the population proportion is 0.88. Usually we don't. Okay? This is from the population proportion. P is 0.88. Okay, so here, centered on 0.88. Okay. No. Oh yeah. So here, what they're emphasizing is that, okay, in this scenario, we pretended to know what the population looked like, right? And that's what we do in the lab as well. We pretend to know what the population is, and then we backtrack and just confirm that the sampling distribution is centered on the population proportion. Now later, what we're going to say is, well, we know that that's the behavior, and so we're going to rely on that. Okay? So this is called the central limit theorem. It's just as important as it sounds. And so sample proportions, so p hats, will be nearly normally distributed with a mean equal to the population proportion p and a standard error equal to p times 1 minus p over n, and then take the square root of that. Okay. And so what we saw, right, is we've seen this shape and we've seen that it's centered on the population proportion. And then we talked about the standard error, but now we have a formula for the standard error. So how we find that standard error. And so we're not going to talk about why this is the standard error, but it is. Okay. And so this is going to be the spread of p hat. Okay. And so we've seen this, and now we just accept it to be true. Okay. And so uh, what happens is that if we look at, okay, so I've got this population proportion P, and then 1 minus P just relies on P, right? So nothing's changed there. And so the only way that I can decrease the spread, right, increase my precision, is to increase N, okay? And so as N increases, samples are going to yield more consistent P hats, okay? Because the spread will be smaller. Smaller spread around P. Okay. So this is this just as important as it sounds, the central limit. It's kind of a phenomenon, I think, where that's always going to be the case, and we can leverage that. But of course, there are a couple of conditions that have to be met. And we're no strangers to conditions, right? We have had check conditions when we use the normal approximation to the binomial. And so now we're going to use those again. They're going to come up again. And so let's see here. How do I know what time it is? Okay. Good. We're still good. It doesn't show me the time anywhere. Weird. Don't remember that being an issue, but that's okay. So the conditions. Okay. So in order for us to assume that we have a normal distribution, which means that we'll be able to find probabilities and areas under the curve and all that fun stuff, right? We have to check these conditions. Now, checking the conditions for you guys is fine because you're all open book and whatever, and but I find it takes up a lot of brain space for how we're just going to do everything anyways. And so so if the conditions aren't clicking, then that's fine. I'll just highlight the key ones. Now, so the first thing that we have to check is independence. Now, so our sampled observations have to be independent. And so the only way that we can kind of assume independence if we used random sampling. Okay. And so just as your go-to condition, you would have to say, okay, I randomly sampled, or the sample was randomly selected, therefore I can assume independence. Yeah. And What's on the flip side? If it doesn't say that the sample was randomly sampled, what would you have to say? You would have to say, I assume the sample was randomly sampled. Okay, and so sometimes I call these conditions, and sometimes I call these or assumptions. Sometimes it's stated and sometimes it's not. And so if we have random sampling or we assume the sample was randomly selected. As in any research, what do you have to do? If you assume something, you have to state it, right? So you have to state your assumptions. Now, for this next one, so we want to have it's common knowledge. We generally know that, okay, we want to have a big sample, you need to increase your sample size, right? And we just talked about how it decreases the spread around your population proportion in this case. And so this next assumption is kind of weird in a way. Because it says if you're sampling without replacement, then the sample size has to be less than 10% of the population, which is kind of counterintuitive, right? We want to have a big sample, but not too big. Why? If the sample is too big, so more than 10% of the population, then there's a chance that you're introducing non-independent observations, right? And that would be a problem. I tend to ignore this one. I don't often check this one because it's rarely a problem, and I just tend to ignore it. I rarely check this one. So you can ignore it if you'd like. But it is a condition, so we should have less than 10% of the population. Otherwise, you're introducing things like siblings and, coworkers, when in fact, we have to be able to assume that these things are independent that we've sampled. But the key one here is random sampling. Yeah? Now, the sample size condition, or I later I'm going to call it the normality condition. So the reason that we can assume that it follows a normal distribution is because of the sample size. And we've seen this condition before in the binomial, right? So there should be at least 10 expected successes. How do you find the expected successes? This is the same as n times p has to be greater than or equal to 10. Huh? What about the failures? 10 expected failures. Well, that's n times q. It has to be greater than or equal to 10. I use q because I'm lazy, but also I want to just use q right away. And so let's talk about what q is. Q is just 1 minus p. Now, q hat is 1 minus p hat. We'll also have a q star, which is 1 minus p star. It's always just 1 minus the p, or its corresponding p. And so I use q, but you're more than welcome to write 1 minus p if you want. N times 1 minus p is the expected number of failures. Okay. One problem that we're going to come up against is, okay, P is the population proportion. Well, the whole problem that we're facing is I don't know what the population is. I'm trying to figure it out, right? And so what you're going to do is we're going to look for the number of observed successes and failures, right? So we just change it to what we have in our sample as opposed to these kind of theoretical ones. We're gonna flip-flop on this a little bit later, but for now, right, just make sure that you have at least 10 successes and at least 10 failures, meaning that your smallest possible sample size that you could have is 20, right? 10 successes, 10 failures, that makes 20, right? That's unlikely, right? Depending on what your proportion is. Uh, So, when p is unknown, yeah, then we said that the standard error, which is the spread, or really the standard error is the standard deviation of p hat, and I'll put a little p hat here, is technically relying on p. Now, the problem is we don't know p, just like we said when we were checking the conditions, right? The sample size or the normality condition. Well, so then n times p, what did we do? Really, what we did was we said, well, hey, what if I just use p hat instead? Right? I don't know p, but what's my best guess for p? P hat, right? And so it's probably on. So then I'll write it here. So then the standard error for p hat is going to be the square root of p hat q hat over n. Save myself 2 strokes, 4 strokes, including the brackets. Okay. And so now, right, in our application, what's nice is to find the spread of p hat. We need p hat, which we'll have as a sample proportion. Q hat is 1 minus p hat, so still no new information needed. And then how did we find p hat? Well, p hat is the number of successes over n. And so usually we have n just as part of the problem. So where p hat is the number of successes over n. Now, the number of successes is often denoted by a capital X over n. Okay? So notice here, X is the number of successes. I mention that because sometimes we have the number of successes and sometimes we have just the sample proportion and the sample size. Okay, and so it depends on what information you have, but sometimes you'll be given the number of successes over n, and then that's how you find your sample proportion. Okay. I'll add, so n minus x is the number of failures. Okay. What if we have some small proportion that we're trying to detect, right? So either the proportion of successes or the proportion of failures. We're trying to get at these tiny things, right? And so if I tell you that the probability of seeing a success is 5%, right, or 0.05, then you wouldn't just go out and collect a sample of 20 and expect to see a success, right? Maybe one, right? But you would have to collect a larger sample in order to see more successes, right? And so that's what we're getting at with that condition. The sample size condition is is that we would need to increase our sample size in order for us to be able to detect the number of successes that we need to see. Okay. So, so suppose we have a population where the true population proportion is 0.05. So we're trying to detect a small proportion. And we take a random sample of size 50. from this population. And so we calculate the sample proportion in each sample, and then we plot those proportions just like we did before. Do I expect it to be nearly normal? And so how we check it is by checking that condition. So no, I wouldn't, because the conditions aren't met, right? And so I need n, which is 50, right? I'll write that here. N is 50 times p, which is 0.5. I need it to be at least greater than or equal to 10. Same with the failures, but in this case, the failures have a 95% probability of happening, and so I'm not concerned about that, right? And so here, the condition isn't met, 2.5 is not greater than or equal to 10, and so then I can't assume I have a normal distribution. And so that's the reason that we have to check the conditions, but for our problems, all the conditions will be met, it's just a matter of checking them. Okay? And so we can look at just kind of how things change as we change our proportion, so our population proportion for our sample size, and how it becomes more and more normal as I increase my sample size. Even for uh, a very kind of skewed distribution initially, right? 0.9, if I collect a sample of size 10, I do not expect it to follow a normal distribution, but as I increase my sample size, it becomes more and more normal. It's kind of a fun phenomenon. Yeah. Uh, uh, I'm gonna ignore the when the conditions are not met because they will be met for us, but you can read through it and that's fine. Okay. uh okay. Do I want to No. Hopefully you had to read through. I don't wanna do this slide. Um, just because I don't want to, introduce, anything but proportions now. Yeah. Okay. So, let me just check the time. Good. Uh, let's start this. We won't get very far. But section 5.2 is we're introducing the first thing that we can do in inference. We've got confidence intervals. Yeah? And so for us, we're just in life actually, in terms of inference, there are two things that we can do. We can build a confidence interval. Just thinking about what that might be, is it's going to have some bounds on. So we have our point estimate, and then we build bounds around it just to find a plausible range for the population proportion. And so here we find a plausible range for the parameter in general. For now, it's going to be the population proportion, but later it's going to change, yeah, to whatever the parameter is. So that's what we're doing here in 5.2. We're going to start with confidence intervals, and then we're going to go to the second part of inference, which is hypothesis testing. I thought you were trying to show me a message or something. No. So hypothesis testing is, I mean, that might sound familiar from grade school. I hypothesize that if I boil water, it'll turn into a gas. That's exactly what we're doing, although not as fun. Well, for me, it's fun, but not as applied, I guess. Hypothesis testing is in the next section, right? Hypothesis testing, I hypothesize that my sample came from a population that's centered on 0.5, right? And then we use probabilities. So that normal curve, we use probabilities to say, that seems unlikely. And then we say unlikely because the probability is so small. And then we can reject that hypothesis, right? And so, and there's many layers to hypothesis testing, but in general, that's what we're doing. And so, uh, test, um, mm, test how reasonable, let's say that, how reasonable a hypothesized parameter is given the sample statistic, or the point estimate, I guess I should say. Okay. We'll start with confidence intervals. So now we're going to find this plausible range of values for that might capture our population proportion. So a plausible range of values, hey, it's almost like I know what I'm talking about. For the population parameter is called a confidence interval. Okay. And so what we think of is usually fishing, right? And so if we just use our point estimate, to estimate the parameter, we would say, okay, well, that's like you're just fishing with a spear. You don't know what the population proportion is, so you just have your one sample and you say, this is what it looks like. Well, that's unlikely, right? And so a confidence interval is more like fishing with a net, right? So you build bounds and you say, I'm 95% confident that these bounds capture this population proportion. It's really important to understand that the population proportion is fixed, right? It exists. We don't know what it is, right? And so, but it is a fixed number. Just like if I, going back to the example, how far is it to my house? And I would say, well, there is an exact distance. I don't know it, right? And so I'm just trying to guess what it might be. So it's really, really important to remember that the parameter, so for the population, it exists, it's fixed, it's never moving, and we're just trying to capture it. Okay, and so so for example, we can throw a spear where we saw a fish and then we'll probably miss it and we won't land exactly on that population parameter, right? Whereas if we toss a net and build some boundaries, right, or some buffers, then there's a good chance, right, that we're going to catch that fish. Okay. Let's see here. Hmm. Do I want to uh okay. You know what I want to do? Just here. Wait, where did it go? Add a page. I want to take us to the formula sheet because that's where I want to pick up next day. And so now, kind of let's zoom out on the formula sheet here. So we moved through descriptive statistics, probability. I'll remember that. We won't have to deal with that anymore until the final. I skipped discrete random variables, so you can cut that. This looks like it might be an old one, but then we have the z-scores. And then we moved into the binomial distribution. I gave you a bonus assignment for the Poisson distribution. And curious to know how that was. I thought it was kind of a fun fun thing when I tried it, but now we're here, one sample proportion. Now, just kind of to give you an overview, right? If you flip to the next page of the formula sheet, right, we said then we're going to move into two sample proportions, right? And look, confidence intervals, hypothesis testing, we do it all over again, a little bit complicated here, but we'll take it in good time. Then the chi-squared is for more than three or more proportions. And then we move into one sample means, and then we move into two sample means, but a special case, and then two sample means, and we'll kind of pick away at this formula sheet. And so this is why I say it's really important that we figure out what type of question we have, and that's going to put you on the section in the formula sheet, and then you can't stray from there. Okay? So what I want to do is just pull in this section, this part of the formula sheet. This is just the general theory of the central limit theorem. You can kind of ignore it. Next day, we're going to introduce the confidence interval. We'll actually calculate a confidence interval. But look, p hat, the sample proportion, z star, we can kind of get there. P hat again, Q hat, well, that's 1 minus P hat n. So there's really no information that we really need, or very little information that we need to build a confidence interval. And then we'll hold off on the hypothesis testing. I know. It doesn't help that we throw in actual Greek letters, right? I know, but we're gonna just chip away at it nice and slowly. And because my voice is not behaving, we'll stop it there and we'll pick up and we'll work through, where is it? This example. But what we want to do is we want to find a confidence interval for this this proportion. And so we'll pick up there, and let me know if you have any questions. I'll see you next day. Stop this.